Okay, so this is the fourth Francqui lecture, and we've already covered environment and growth, energy and growth very broadly. And last time, a month ago now, we looked at the economy-wide rebound effect in some more detail. And this time, I'm going to look at energy and industrial revolution. So again, perhaps a bit, I know it's a big topic, of course, but a bit more focused than the first two lectures. And there's also some material a bit more technical, but I've tried to make it quite approachable. Let's see, I've got to find my slides and I'm going to have to share them. Share content.
Maybe I use then this time to briefly emphasize the next lecture on May 7 about econometric modeling of global climate change, and also to emphasize with regard to GDPR that this lecture is recorded, and I will put in the chat where you can find the recording. And so by staying with us, you agree that we upload this video later on. Yeah, so that's it from my side. So the floor is yours.
Does that look good? I'm pointing in the right place. Okay.
Looks perfect.
Where are we here? Right in the middle. That's no good. All right. Energy industrial revolution. All right. What is going on here? Okay. There, that's more like it. Introduction to energy and industrial revolution. So what do we mean by the industrial revolution and what happened before it? So this is Britain. Britain was the first country to experience it, the Industrial Revolution. And this goes way back 2,000 years. Of course, the data before about 1200 are extremely sketchy and largely reconstructed after 1200, 1270. Population grew very slowly, and then it began to grow in the early Middle Ages a bit more substantially. And then there was the shock of the Black Death, and the population greatly reduced. And we look at what happened to GDP per capita. GDP per capita is estimated. This is based on the Madison project at University of Groningen in the Netherlands. You can download their database. It was pretty much constant this whole time. But interestingly, the population was growing. What happened after the Black Death is there was an increase in GDP per capita. And the reason for this is suddenly there was more land per person. And the diminishing returns of adding more people to land was suddenly repealed. You had less people per unit of land, and output per worker actually increased. So actually, even though the Black Death was bad in terms of the destruction of life that that's happened, after the Black Death, the people who survived are actually better off. But then we see after that period, population eventually begins to start to take off again, but not much happens there, or maybe even GDP per capita is estimated again by economic historians is drifting down. So we see the same patterns. We begin to build up population, nothing happens to GDP per capita, or it falls, but when population falls, it can bounce back. Then suddenly something new happens. This is the Industrial Revolution. GDP per capita starts rising, and population's rising at the same time. So this is a new thing. Population and GDP per capita are rising. Of course, then things just go crazy, exponential growth. I think this data ended during the financial crisis 10 years ago. Given the long run history here, it wasn't very necessary to update it. So something very new happened. Population and GDP per capita began to grow rather than being kind of in competition with each other. Energy use, this is zooming in, of course, into post-1560 periods. There was a data set by economic historian Paul Ward at Cambridge University has reconstructed British energy use back to 1560. Initially, it's pretty flat. And then around the late 17th century, it begins to increase and increase faster and faster until the end of the 19th century. After the 19th century, Britain, a bit unusually compared to most other countries, hasn't actually really seen much increase in energy use per capita. It was one of the most energy intensive countries in the world probably the most energy intensive, around 1900. And so in the framework I gave in lecture 2, it's been really converging back towards what other countries in the world, energy intensity in other countries in the world during this time, over the subsequent century. Anyway, the key thing here is there's an acceleration of energy use at the same time that GDP began to grow as well as population. And these seem to be, look like they could be connected things. Looking at the whole of Europe, the rest of Europe experienced industrial revolution later than in Britain. Energy use per capita is flat till the mid-19th century. Only then does it begin to increase, and it's increased more in the subsequent period than it did in Britain. These countries are really, everywhere else in Europe but Britain, are catching up to Britain where the Industrial Revolution started. So thinking about the pre-industrial economy, that's up to the Industrial Revolution here, where energy use was fairly constant. What is going on? Well, energy use was dominated by biomass. By this we mean wood for fuel, and we mean animal and human power for power sources. Turns out water and wind, though we might think of them as being important, and maybe it's a few countries like the Netherlands, they were particularly important, but overall they actually contributed relatively little to energy use. It was dominated by fuel wood here, mainly wood, and food for humans to produce muscle power from humans, labor power, and fodder for animals, for animal power. So it's totally dominated by sources from biomass, whether it's food or wood fuel. And the problem is that there was only a low yield of useful work from each square kilometer, because plants are very inefficient. Converter of sunlight only convert about 1 or 2% of the sunlight into sugars, into usable energy, compared to 15% or more for voltaics. And sunlight really is quite diffuse. And to do farming, you need lots of labor power or animal power, and animals and humans are inefficient converters of plant energy into power, and so you end up with very low energy return investment in farming for the amount of energy you're actually putting in. And other technologies like metal smelting, etc., also very inefficient in this period. And so the output of energy is limited by how much the land can grow, and it's really quite low productivity. City size also was limited by transport costs. Transport was very expensive, animal power or small ships, and basically how much food you could bring to a city. As a result, little surplus left to invest. Often, of course, there was little security for your investments due to the amount of war and other things going on, general violence, and so tended to be that population was higher in areas of higher productivity. So the most populous country, I think, in Europe in the pre-industrial period was Italy, which had a warm and climate with reasonable amount of rainfall. The population of Britain was a quarter of that of Italy. Today, of course, they're quite similar. Britain might even be a bit bigger. And in Sweden and Finland, places like that, Finland had very little population before the modern era. Okay, so that's sort of thinking about the pre-industrial economy. So what can get us out of this low productivity situation? That was, some economic historians think, was coal, because certainly there was a very concentrated source of energy, which could produce much more energy per unit area, and which, when used in machines, and those machines developed to be more efficient, resulted in a much more high productivity from a given energy input than the pre-industrial economy. But there's a debate how important coal was in the Industrial Revolution. The average person probably thinks it must have been important, and some economic historians think it was important, but others, particularly Gregory Clark, who's a very well-known economic historian, argues it's negligible. They argue coal was a relatively small part of total output, and if Britain hadn't got coal, well, it could just have imported wood from Scandinavia. There hasn't ever been a very big international trade in firewood, though, because it was bulky and expensive to transport. They argue, well, it would have happened. So their argument is that there's nothing special about coal versus wood. There's another paper in Journal of Economics on 4 centuries of British economic growth, Madsen et al. They conclude also that coal had little impact on economic growth in Britain, but that's what you find if you control for the level of patents. So they control in their regression models for level of patents. If you have more coal for a given amount of innovation, maybe it doesn't have very much, but maybe it was coal that allowed a higher rate of innovation. Also, they look at annual differences. They don't look at very long run effects. So I'm not, you see, I'm not that convinced by this literature that says that coal wasn't that important. On the other hand, Wrigley argues that coal is extremely important. He compares the Netherlands to Britain. If you looked around about 1600, both the Netherlands or late 17th century, both the Netherlands and Britain seem to have good institutions that favor development of markets. They both had trade networks and both seemed to be going in a good direction. But Britain took off in the Industrial Revolution. Netherlands didn't. The argument is, well, Netherlands didn't have coal. They did have peat, but peat seems to be more costly to extract than coal would be his answer to that. Allen's argument's a bit more subtle. He also thinks that the availability of coal was crucial to the British Industrial Revolution, but he argues it was because British wages were already quite high relative to the cost of energy, that it was profitable to use coal in Britain, and it wasn't profitable, say, in Germany in the same period, because German wages weren't as high. Why were British wages high? Doesn't really explain that, but perhaps it's because of the starting of trade and the British Empire in its early period managed to boost the wages of British people higher by using resources from other countries, cotton and so forth, to produce industrial goods in Britain. Before, cost of milling in Britain was driven by water power before takeoff of coal. So there's a debate here about, let's go to the right place here. Looking at research that's used growth theory, which is more similar to what I'm going to do in the couple of papers I discuss in this presentation. There's a paper in the American Economic Review almost 20 years ago by Hansen and Prescott. Prescott's a Nobel Prize winner in economics. And they have an economy with 2 sectors. One is based on land, and so increasing all the other inputs, capital and labor, apart from land, has diminishing returns or decreasing returns to scale. On the other hand, there's a non-land-based sector where there's just capital and labor used, and that one therefore has constant returns to scale and so can grow faster than the land one. Initially, though, it's not profitable to use this non-land-based technology, so they make an assumption that technological change is faster in that non-land-based sector, which they call the Solow sector after Robert Solow, whose economic growth model in 1956 is still sort of a central model in economics of growth. And the land-based sector they call the Malthus sector, referring back to Malthus, who said the population would overtake the increase in the means of production, and the economy would really, in terms of living standards, stagnate. So I have these 2 sectors, but there's a switch happens from the land-based sector to the non-land-based sector because they assume technological change is faster in that sector. So it's an automatic result. Fröhling doesn't use exogenous changes in technology, just endogenous changes in technology, which is maybe a bit more promising, and 2 different energy sources. So she explicitly models biomass and coal, but assumes that technological change only can increase the productivity of coal. Well, once she makes that assumption, again, there's naturally going to be a transition from biomass to coal eventually, because the productivity of using coal gradually increases to the point where it is better to use coal than biomass. And Okay, so again, a similar assumption. Most of this literature is making assumptions about how cheap it is to innovate in different sectors or how fast technological change is in different sectors. The paper that's probably closest to what I'm going to present is published only 2 years ago in the Journal of Economic Theory, Gars and Olofsson. They have endogenous technical change. The technical change responds to incentives. They have 2 energy sources, biomass and fossil fuel. Their fossil fuel stock is actually increasing because of discoveries rather than decreasing because of depletion. That's not so important. What they assume, though, is it's cheaper to innovate in innovations that make fossil fuels more productive, that augment fossil fuels. And it's also cheaper if you're nearer the technological frontier. That means in the more developed countries, it's cheaper to innovate than in the less developed countries. So they apply their model just to a single country. That country automatically ends up using fossil fuels because it's cheaper to innovate in fossil fuels. But when they look at a bunch of different countries with heterogeneous technology levels, so there's some low technology countries and high technology countries, because it's cheaper to innovate near the frontier, and the demand for fossil fuels from the developed economies make fossil fuels expensive, the low technology countries end up using biomass and their economies stagnate. But again, here we got an assumption about the cost of innovation, which is driving results. So we wanted to see if you could get a transition from, here there isn't actually a transition, there's just countries stuck using biomass and countries that switch to fossil fuels, only use fossil fuels. I want to see if you can actually model a transition from biomass to fossil fuels without making any assumptions about which sector it is easier to innovate in, whether it's easier to innovate to increase the productivity of biomass or easier to innovate to increase the productivity of fossil fuels. We don't want to make that assumption. It may be true, but it's easier or cheaper to innovate with fossil fuels, but what happens if we don't make that assumption? Okay, so to go there, we have to look at, whoops, I'm still sharing, hopefully. Is that okay?
Yes, we can see the slide.
Okay, all right, I clicked on something and something happened, but yeah. Okay, so to do that, we use the theory of directed technical change. And so what is a direction of technical change? So direction of technical change means what is the rate of technological change faster in some sector of the economy than another sector of the economy? Or is technological change increase the productivity of some input, say energy, faster than technological change increases the productivity of another input like labor? And now I can't, now what happens? I have to go back to this screen. Okay, so the question is, what determines that direction of technical change? Well, going back to 1932, Hicks, famous, again, another Nobel Prize winning economist, his book, The Theory of Wages, he introduced the idea that there was induced innovation. The price of an input like labor increased, then firms would want to reduce their use of that input. They could do that by just reducing it, but they could also do it by innovating to make the productivity of that input higher. In the more modern, that theory was never that well developed, but 20 years ago, Daron Acemoglu developed a theory of directed technical change. I think probably more important than people probably know Acemoglu more for his work on institutions and development, but I think his work on directed technical change is probably more, I think is probably more important. And so this is the modern theory now of what drives technology in one direction or another, at least in a simple way. So the crucial parameter in this theory is elasticity of substitution, which we designate sigma. I talked about this, I think, in both the last 2 lectures towards the end of the second one, and in the discussion of rebound effect. The elasticity substitution between energy and other inputs was kind of crucial. And here again, the elasticity substitution between energy and other inputs is going to be crucial. So as a reminder, elasticity substitution reflects how hard it is to replace one production input with another one when one becomes relatively more scarce. So when the price of one input increases relative to the other, how does the use of the two inputs change? If it changes a lot in response, then there's a high elasticity substitution. If it changes little in response, there's a low elasticity substitution. It's hard to substitute one input for another. Now, if this elasticity is greater than 1, neither input is essential. You can actually get by with just one input, okay? But if it's less than 1, then both inputs are essential. So you need minimum quantities of each. So we tend to think that energy is really essential. On the other hand, is coal or wood essential? Maybe not. Maybe you can use wood instead of coal, or coal instead of wood. So what the elasticity substitution is will depend on the sort of nature of those inputs. And we're going to argue that, as we argued last time, that energy, probably elasticity substitution with other inputs less than 1. Here the crucial thing is going to be that coal and wood, at least in the long run, are probably quite substitutable. You can replace one type of energy with another type of energy. So here's a production function that an elasticity substitution of less than 1. This is designated this one capital and energy. And the idea here is that these are curves of constant output. So we go up here, we have more output. They're called isoquants in production theory. They're very tightly bent here. So there is some trade-off between the two inputs here to get the same level output. But when we go to holding the level of capital constant and using more and more energy, we actually get very little extra output for that additional energy use. And so we're quite close to having to use capital and energy in fixed proportions. The elasticity substitution here is very low. By contrast here, the elasticity substitution is greater than 1, and you see these lines of constant output, the isoquants actually cross the axes effectively, and so you can get by using just one input. If you have 0 capital but have this amount of energy, you actually have a positive level of output, the same as if you had some mix here or just capital and little energy up here. So this has got a lot of flexibility in production. You don't have to use capital and energy in near fixed proportions. So that's just with elasticity substitution what it implies, because that will be important. Acemoglu's, we got some. Oh, that was just Stefan. All right. So Acemoglu's theory's got 2 sectors, so that makes things still tractable. And this is the output of 2 sectors or 2 intermediate inputs in the economy. And in these original papers, each of these has a specific input. In these original papers, one is unskilled labor and skilled labor, W and Z. But in our approach, they're going to be wood and coal or capital and energy. It doesn't matter really. So the 2 sectors of the economy which you intensively use, or 2 types of intermediate inputs intensively use a particular input. And there's also technology here. AW is a technology that reflects the productivity of using this input W, and AZ is the technology that reflects the productivity of using the input Z. And then we have a production function, uses this technology with this input and produces this output. Then there's the top level production, final production. We take the 2 intermediate inputs, YW and YZ, and combine them. And this is where the elasticity substitution comes into play. Is it easy to substitute the outputs of these different sectors or these different intermediate goods, or hard to substitute them? So basically it comes down to a directed technical change model. The main result is if W becomes scarcer relative to Z, so the price of W rises relative to Z, if the elasticity substitution is greater than 1, innovation in the technology associated with the input that's now more abundant becomes relatively more profitable. And the intuition here is that it's easy to substitute one input for another. So if one is getting expensive, we then find ways to use the other one. and which is now much cheaper to use. And because they're easy to substitute one for the other, that turns out to be more profitable. On the other hand, if elastic substitution is less than one, it's hard to substitute one input for the other. Then, in fact, innovation focuses on making the input that's become expensive more productive. This is what Hicks argued originally. But if the price of an input rose, innovation would focus on making that input more productive, and so we could use less of it. The theory of directed technical change shows that that depends on elasticity of substitution, and you can have actually the opposite result. This actually turns out to play out pretty well empirically for an economic theory. Some of them maybe don't. So it's a very flexible theory, and we can use this to explain energy transitions, which I'm going to do here, and also whether energy efficiency is increasing or not, which we talked a lot about last lecture. So the rate of improvement in energy efficiency. Okay, so basically whether we innovate to increase the efficiency of energy use or the efficiency of labor or capital use. That's going to determine whether energy efficiency increases rapidly or not. And we're going to apply here first the British Industrial Revolution and then to growth in 19th and 20th century Sweden. So this is more a theoretical model, and this is more of an empirical analysis of what factors led to growth in Sweden, how that changed over time. The first application got wood and coal using sectors, and a sort of traditional sector and a modern sector. It's easy to substitute between the outputs of these sectors. Wood becomes scarcer relative to coal. Oops. And innovation shifts to technologies that use coal, the increase in the abundance sector. How do we know it's easy to substitute coal for wood? Well, because they did it. They pretty much replaced wood use or biomass use or animal use with fossil fuels. So it seems to be easy to substitute one for the other. In the Sweden case, we're going to look more at all energy versus other inputs. And it's going to be hard to substitute other inputs for energy. Energy per worker increased over time because energy is once you switch to using coal and other fossil fuels, energy is very abundant. And so, in fact, labor is becoming relatively scarce. And so innovation turned out to increasingly go to increase the productivity of labor rather than energy over time. This might not sound right to you, but that's what the data actually show. So so that was just a summary. This is Iron Bridge in England. Coalbrook Dale, where iron was first smelted with coal, is where this, is where this whole cloud of smoke is coming from behind the Iron Bridge, which is the first bridge built entirely from iron, because now iron was cheap after they switched from using charcoal to smelt iron to switch to coal to smelt iron, which this happened early 18th century in England. I already sort of looked at the long run. Yes, GDP per capita increased from about the 17th century on, particularly in the 19th century. And look at the growth rate. It wasn't a smooth path. So the growth rate's increasing, but it's still something of a rough path. So there wasn't like a massive acceleration in growth. It's more of a slow, gradual increase in the rate of economic growth. So what actually happened to the scarcity of coal and wood? So here, these are prices actually for charcoal rather than wood itself. And therefore London, which London was far from the sources of either coal or of wood, and the Western UK, where there was abundant coal and wood initially. So in the Western UK, prices of both are very low here compared to in London. So already in London, these inputs are relatively scarce. They had to be transported to the city from west and north of the country. The price of charcoal rose a lot in London, became very expensive. A bit later on, it became expensive even in the west of Britain. On the other hand, if we look at the price of coal, it remained fairly constant in London over this whole time period, certainly compared to charcoal. And in Western Britain, it maybe even fell. It was fairly constant. What's going on here? Well, coal mines are are getting deeper. Steam engines are helping pump water out of mines. Steam engines are helping extract coal from mines, and then railways to transport the coal and so forth. And so the price of coal is not increasing because they're using more and more coal, in fact, and more efficient machines using coal to help produce coal and dig deeper and extract more coal. Population increased, particularly again after around 1750, quite rapidly. What happened to energy use? Well, firewood was pretty much constant according to Paul Ward, and then in the 19th century collapsed pretty much to nothing as a practical source of energy. With coal use, this is a log scale, coal use grew exponentially throughout the period. So huge. So there's coal use in Britain going quite a way back, but the level was quite low back here. It wasn't until late 17th century there was more coal than firewood use. Energy intensity also increased. So we talk about energy intensity declining in developed economies. Well, initially before 1900 in Britain, it increased. And when we look at just firewood and coal, it increased a lot as the switch happened from firewood to coal. Because coal's so much cheaper, they could use much more of it per unit output. If you include animal use and labor, total energy intensity, well, that didn't increase by quite as much, but it still increased from a point of industrial revolution onwards up to 1900. So we're going to now sort of dig deeper into the directed technical change model, apply it to this specific application. So we use the original model that's in Acemoglu's paper, but instead of skilled and unskilled labor, we use coal and wood. And over time, there are more expanding product variety is actually expanding machine variety. So new types of machines are being developed, like steam engines or coal-fired blast furnaces or whatever it is, which use coal, or new varieties or improved varieties of machines which use biomass. There are two sectors based on the Hansen and Prescott paper. We call these the Malthus sector. So the M for Malthus, this is the wood-using, biomass-using traditional sector, and the solo sector, which here explicitly does use coal. Okay. By the way, we're only modeling up to 1900, because after 1900, oil comes in, and then primary electricity and all kinds of things. So we're in another world after 1900. So we're looking at the transition up to 1900. So we got a coal-using sector, which we call the solo sector. Each has an energy input. We do make an assumption there's a difference between these sectors, that wood is available in constant quantity as like its maximum sustainable yield of wood. And the reason we make this assumption is simply that that's what the data show wood use was constant. Okay. On the other hand, we assume that coal is available at pretty much a constant price. And the reason we make this assumption is because data seems to show that coal was available at pretty much constant price throughout this period. We don't actually model those sectors, the actual production of wood or coal. What we're modeling is downstream where those inputs are used. Here we just assume population grew exogenously, just to keep things simple and focus on the mechanism we're interested in. These are the actual equations we use for the production structure of the economy. A simplified version is this, this is the notation we used in the introduction. There are two intermediate inputs which are used to produce final output from the economy, and they can be substituted one for the other. Elasticity substitution is greater than 1 sigma, and then these two intermediate inputs are produced. This one's produced using wood. This one's produced using coal. This again, Solo's coal, Malthus is wood. Both of them also use labor, and labor can flow between sectors. The actual specific functions is this. This is a constant elasticity of substitution production function. So this elasticity of substitution sigma is the crucial parameter that figures in here. So this is the output of this sector. This is the output of this sector. They combine into the final production. In each sector, we have these machines, X, okay, sorts of machines. There are NM numbers varieties of machine in this Malthus sector. And that number is going to change with technological change. There'll be new types of machines developed. In this sector, there are, in the coal using sector, there's these special coal using machines, and that NS types of these coal using machines. And that number is going to increase with technological change. Then we have the input of wood here, use of labor, and the input of coal here, and use of labor. The crucial thing here is the difference we assume is not how easy it is to innovate, it's that coal is available in as much as you want at a fixed price, whereas wood is fixed in quantity. So yeah, we are biasing it towards coal use, but that is based purely on data we can actually observe, rather than speculation about which sector it's easier to innovate in. The innovation is quite simple. So there's resources used for R&D, expenditure on R&D in each sector. And each period, each time step, a time step is 20 years in this model, each period there are diminishing returns. So new, this parameter here is less than 1, between 0 and 1. So there's diminishing returns to expending on R&D within a given period in each sector. But we assume that new and eta, these parameters here, are the same in both sectors. So we don't assume it's easier or cheaper to innovate in this solo coal using sector than it is in the wood using Malthus sector. It might have been, but we don't assume that. We don't have any data on it that I'm aware of, good data. We make assumptions, perfect competition, the final output, in the sector outputs, in machine production, but there's a monopoly in developing new varieties. So you can effectively have a patent, or even there wasn't a formal patent, you could hold on to the profits from innovation for a while. So that gives incentive to innovate. When you combine these assumptions, the production functions, the innovation functions together, you end up with this equation. This equation says pi is profit from innovating in the wood using Malthus sector, and pi s from innovating in the coal using solo sector. So there's the relative profitability innovating in the two sectors. It depends on the relative price of output in each sector. If the price of output in a sector is higher, okay, it's more profitable to innovate in that sector. There's a high price, okay, high price of goods you're selling. If the size of that sector is bigger, because you can use one innovation across a whole sector, it's profitable to innovate in that sector. On the other hand, we're diminishing return. This is the intuition. This was all derived from those equations back there, right? On the other hand, they're diminishing returns to knowledge accumulation in each sector. The more knowledge you might get in a sector, the less additional knowledge is adding. So there's diminishing returns to this. You can write this equation out as using these symbols here are just a ratio, each of these ratios, okay? So that simplifies the notation in the graphs I will show you. So this is basically what I just said. Now the thing is, as an energy resource becomes more abundant, production tends to shift towards the sector where energy resource is used in. Just because it's cheaper, there's more energy being used there. Because the relationship between P and Y, the ratio of prices times the ratio of output, the ratio of revenue in the two sectors turns out to be equal to this. And this is simply derived from perfect competition and the final production function. Because of that, the higher sigma is greater than 1, incentives then shift in the same way to the sector whose energy resource become more abundant. And that's what we're assuming. It's greater than 1, based on that we actually managed to replace wood with coal. Okay, we can show also that the rate of technical change, this is the rate of increase in the new types of machines, percentage change, the ratio that across the two sectors also proportional to these same factors, okay? Now it turns, so little n is the relative rate of technical change in the two sectors. So that's a direction of technological change. And it turns out that if sigma is less than this function of parameters, and these are parameters from the production function, the share of capital and the share of energy is alpha, share of capital is beta. And 1 minus alpha minus beta is the share of labor. in production. If the elasticity substitution is less than this, then there's only one path of economic development that happens. And this is it. So on this axis here is a ratio of knowledge in the two sectors, with the wood using sector above. So we're moving in this direction. We're getting more and more knowledge about using wood relative to knowledge about using coal. In little y was the ratio of output of the two sectors. So we go in this direction, we're more and more specialized in wood using production rather than coal using production. If we go in this direction towards the origin, we're going to more and more coal, more and more focus on coal output, coal using output, more and more focus on coal, knowledge about using coal, and the Industrial Revolution is going down towards the origin here. But if we start over here, with relative somewhere in this point like this, initially the economy actually tends to develop. So actually it becomes more specialized in the direction of outputs using wood initially. And that turns around and eventually ends up heading down this direction where we're more and more coal using knowledge and more coal using output relative to wood using output. Why is that? Well, initially, the incentives are in favor of a wood innovation, but because coal use is expandable and wood use isn't expandable, there's a little bit more growth happening in that coal using sector every period. And eventually it begins to turn the direction that sector is beginning to, even though initially the incentives were in favor of going in the wood direction, the incentives begin to favor shifting towards the coal using sector, just because coal is getting more and more abundant. Okay. So summarizing here, because coal supply is infinitely elastic and wood fixed, we already said this, rising wood scarcity increases the rate of economic growth. That would be the case, but it also more and more coal abundance, because you can extract unlimited amounts of coal. On the other hand, if the elasticity substitution is greater than this value, then there turn out to be two development paths. One's this Industrial Revolution path we already discussed, and the other path actually is pre-industrial stagnation, which in fact becomes more and more wood specialized and doesn't turn around to Industrial Revolution. So if we have a lot of wood initially, we can end up on this pre-industrial stagnation path, and actually coal use falls. This might represent China in the second millennium, and whereas the Industrial Revolution path is Britain in the second millennium. So it turns out that actually having less wood, less flexibility in production, so you have a slow elasticity substitution and less wood, actually puts you onto this coal using path. Now, which has faster, where economic growth accelerates because coal supply is infinitely elastic, and there are therefore constant returns in production in this coal using sector. So this is a diagram with two development paths. This is the path I already told you about. This is the pre-industrial stagnation path. So basically down here, for the relative to the knowledge stocks, there's a relatively large amount of wood using output already, and that is because wood is relatively abundant. So if you're below here, it's because wood is relatively abundant relative to the knowledge about using the two stocks. And if you're down below this line here, you end up going in this direction and never turning around. You get more and more wood specialized. So why is that? Well, it's proved very hard to explain to the referees. I'm not sure I'm managing to explain it to you either. This paper is actually now in press, the Journal of the Association of Environmental Resource Economics, JERI. But yeah, it's proved quite hard to explain. So the direction of technical change, as I said earlier, is the relative rate of technical change in each sector is proportional to the relative output in each sector. It's the power of this function of elasticity substitution. this is the new, remember, was a innovation parameter, but it's declining in the relative knowledge stocks in each sector. Basically, if we sort of take logs of this equation and take differences of this equation, we end up with this. The rate of relative technical change in the two sectors is equal to this function of elasticity substitution times the effect. Now, basically what is driving output in the two sectors is a relative knowledge stocks in the two sectors. So if the knowledge stocks in two sectors shift, then output shifts in the two sectors. Remember, coal use is endogenous here and wood use is fixed. So we're not seeing shocks to wood use or shocks to coal use that are driving anything. It all sort of happens endogenously. So this first term here, this is the rate of growth of relative output in the two sectors. Well, is this elasticity multiplied by the relative rate of change in the knowledge stocks of the two sectors. And then this is the logs of this term. It's a rate, again, the rate of relative change in knowledge stocks into say rate of technical change. And this is greater than 0, and this elasticity here gets bigger. It turns out, we show in the paper, the greater this elasticity is greater, the greater sigma is, greater elasticity substitution is. So basically, at some point, the contribution of the relative output in the two sectors overwhelms the diminishing returns to knowledge here, and you end up with the change in the relative rate of technical changes getting more and more and more big over time, more and more in the direction of wood specialization. And it only happens when you start the right point and have a high elasticity substitution, because you also multiply by this factor here, and this elasticity also increases with higher elasticity substitution. So this is positive forever. You get more and more locked into increasingly wood-directed technical change, and that is happening in this zone down here, which is where wood is relatively abundant. To find yourself starting at that point, you have to have relatively abundant wood. Okay. So that's got a paradox. So maybe it shows something about the resource curse as well. Why do countries with lots of resources maybe don't develop as fast as ones that were poor in resources, like England? England didn't really have much going for it. And in Asia, Japan is maybe a country that didn't really have that much, lots of mountains of trees on, but not much in the way of other agricultural land or coal resources, only small coal resources. So it's not just theory. We do a simulation. We assume a very high elasticity substitution. Of course, we also do a robustness, sensitivity analysis of this. We take the share of energy and costs. We base these on the literature. Energy was a large share of costs in the early, in the pre-modern, early industrial revolution period. Then we sort of normalized some parameters in the model, and others we optimized. We fitted it to the data from Britain very roughly, the data available, to actually show initially the knowledge about using wood was much higher than the knowledge about using coal. And then some things are just parameters that are fitted, like the price of coal. This is our baseline simulation. It should look something like what really happened, because we optimized some parameters to fit it to the data. So what we see happening is the price of wood relative to coal rises over time. It peaks eventually and falls, okay, later than in the data, but it does turn around and fall. The use of coal, this is the log use of coal. Use of coal eventually is exponential, even faster than exponential at some point here. GDP per capita is pretty stagnant before taking off, again a bit later than when we might like to see it, taking off and accelerating after some turning point. On the other hand, the use of labor in the wood using sector falls down to about 0 over time. So there's a transition out of the wood using sector to the coal using sector. The this is not realistic in the sense that things happen too rapidly. This industrial revolution happens more rapidly within practice. But we perhaps if you didn't make the rate of innovation equal in the two sectors, the ease of innovating, you might be able to fit the data better, the model better to the data. We maintain that assumption, even though it might not be a true assumption. On the other hand, we assume 10 times as much wood and run the same simulation. This is what happens. GDP per capita, this is a population growing as it actually grew exogenously here. GDP per capita doesn't take off. There isn't a transition really out of the wood using sector, and the wood price starts much lower and increases, but that doesn't peak within this period. So having abundant wood definitely delays the industrial revolution here. This is no population growth. Almost nothing happens within this time period. You need to run the model for millennia or something to get a takeoff to growth. And this is a scenario which looks very similar, where actually coal use is falling. You can barely see it. You can see it stepping down a little bit here. Coal use is actually falling in this scenario here. So necessity is the mother of invention, as I think it was Plato or Aristotle, I'm not sure which, who said that. Resource scarcity hastens the industrial revolution. This model, we used sort of standard growth theory model with some basic facts that seem to be apparent in the data, and it seems a plausible explanation of what happened. Abundant renewable energy and high flexibility can lead instead to stagnation. You don't need to assume a coal sector is inherently more productive to get these kinds of results. Hey, there's the Iron Bridge today. It's still there in Shropshire in England. Okay. So that was a theoretical model applied to the Industrial Revolution in Britain, and then sort of simulation to see how well it explains what was being observed and what would happen in counterfactual simulations. And then we're going to go on to a paper we actually published back in 2012 in the Energy Journal. I published it with Astrid Kander, who's an economic historian in University of London, Sweden. And it's much more empirical. We fit the production function econometrically to annual data over 2 centuries from Sweden. This is a big copper mine in northern Sweden, by the way. Okay, so what happened in Sweden? Sweden developed later than Britain. And you see energy use really taking off. This is, orange is, again, log scale. Really starts to rate more only really in the late 19th century here. We only have data on capital from 1850 on in this data set. And the GDP actually was growing quite, it's even hard maybe to see the acceleration in GDP growth in this period, but there probably is a little bit of it. And as the GDP growing, capital grows, energy grows, labor use grows, but much less. There's more energy per worker. Energy volume is an index number for energy that takes into account the energy mix. So in Sweden, that actually grew by more than energy use. There's a shift to more expensive sorts of energy over time. That matches the GDP a bit better than energy use. So all this is reconstructed data back here from these economic historians. Oops. This shows a transition of energy use in Sweden. Back in the early 19th century, huge use of fuel wood, animal and human power. And then coal only comes in around 1850 in Sweden, becomes dominant, and then we shift later to oil, primary electricity. You see the effects of the world wars here, switching back to fuel wood when imports of coal or oil were not possible. But yeah, that's the sort of long run energy transition happened in Sweden. The energy, the interesting thing, and what actually got me interested in this originally, I saw Astrid Kander's PhD thesis, and she had a graph something like this of what money spent on energy relative to total expenditure in the economy over time. And well, here it shows it greater than the GDP, but that's because energy is an intermediate good. So that's possible. was very, very high in the 19th century and declined over time to a low cost share today. And that's really a dramatic transition. That only would have happened if the elasticity substitution in energy and other inputs is less than 1 and energy is becoming more abundant. So that's the citation of the paper. So in this model, there are 2 inputs: there's capital and labor as a sort of composite. That's sort of your solo kind of model, just capital and labor, no energy input. And then there's an energy input, which is just for this energy index. It's adjusted for the quality of energy use. Elasticity substitution is less than 1 we estimated. We find that it's 0.67. So again, there's the top level production here. It's sort of labor intensive output and energy intensive output. This is substitution between them. And because it's not equal to 1, the energy cost share, sigma is not equal to 1, energy cost share can actually decline over time. So we know it's not equal to 1, there's been a dramatic decline. This is the function that produces a YL output. It's just capital and labor and some labor augmenting technology. That's like a very standard solo growth model. And then the energy use and its quality index and energy augmenting technology. Okay. So we estimate this production function together with some other equations, first order conditions. We estimate from that the elasticity substitution and the rate of exogenous technological change, which should let vary over time. And then we simulate this model together with the estimated model together with capital accumulation equations. It's really a solo type model augmented with energy. And these are the results. Okay, so there's no real skipping sort of a theory stage. So elasticity substitution is about 0.67. So this first row here assumes a constant rate of technological change over time. So energy augmenting technical change was about 1.9% a year over this period. Well, labor augmenting technical change, which is what most economic growth textbooks focus on, it was only 1.2% over this period, according to our estimates. These are standard errors under here. Then we allow the rate of technical change to vary in each period. And we split it into 50-year periods, 1850 to 1900, 1900 to 1950 to 2000. Again, before 1850, we don't have capital data. We didn't have capital data, so we simulated the model back there, but we didn't have data to estimate back there. So we find the energy augmenting technical change was very rapid in the 19th century, 3% a year. And then it fell in the later periods to lower rates of 1.4, actually an increase here, 1.9. Labor augmenting technical change was actually, turns out here to be negative, which is a bit of a surprise. We didn't account for changes in labor hours, so perhaps this is reflecting when actually we've got number of workers and the hours per worker was declining in this period. And there wasn't really much labor augmenting technical change. What happened in subsequent periods, though, is the rate of increase in productivity of labor augmenting technical change increases to 1.2% and then 2.1%. So it's faster by the end of the period, end of a sample, than energy augmenting technical change. Whereas back in the 19th century, energy augmenting technical change is faster. Now this fits our directed technical change theory. Once energy became abundant and more and more energy per worker, eventually the innovation shifted increasingly towards labor, because it was labor, initially energy was scarce, and then later labor is a relatively scarce factor. So innovation shifts from augmenting energy, the relatively scarce factor, to augmenting labor, which becomes a relatively scarce factor. So the simulation, of course, the baseline simulation fits the data very well. Well, that's not a surprise, we fitted it. We estimated the model econometrically. So this is GDP. What's interesting is when we do the counterfactual simulations. So here we held constant energy. Well, we allowed technology to change, and we allow labor to change, capital to change. So capital is endogenous though, but we allow basically just holding this energy quantity constant. and we see the lines diverge. We get less growth if energy use was constant. The point where these lines are most divergent is in the sort of late 19th, early 20th century here. Later on, the lines are again more parallel, perhaps. So energy was most, holding energy constant most slows down economic growth in that period. So we observed that energy is most important in that period, expanding the use of energy. If we look at energy quality, seems like it was the shift to higher quality energy sources that was most important, early 20th century, perhaps when we see the shift from coal towards oil happening. And if we look at energy augmenting technical change, this has a dramatic effect, but particularly in the 19th century, late 19th century here, without energy augmenting technical change, there's pretty much no growth at all in this period. However, in these later periods, you can actually get quite a lot of economic growth without energy augmenting technical change because there's labor augmenting technical change now. Okay, so everything, we only hold one factor constant and hold everything else according to what we econometrically observed in the data. Finally, holding labor augmenting technical change constant, or estimated, it had no effect back here in the 19th century, but it increasingly has an effect in the late 20th century. So labor augmenting technical change becomes increasingly important. This results may be quite different to what sort of people might on average kind of think about what is going on. We're using energy more efficiently now because of the oil crisis and the climate crisis and so forth. Well, yes, it is improving, but what's really driving economic growth is increasingly what the economic textbooks say is driving economic growth, which is labor technical change. And basically the economic textbooks focus on this, mostly on this post-war period. Most of the growth literature focuses on this, doesn't focus much on the economic history back here. And so it's reasonable to say that energy is not very important and labor augmenting technical change is a driver of economic growth. It really seems to be true in this recent period. But energy was much more important in getting the Industrial Revolution going. So we can then use this to get an annual percentage contribution to growth of each factor in each 50-year period: capital, labor augmenting technical change, energy augmenting technical change, energy use, energy quality, energy augmenting technical change, and they all sum up to the rate of economic growth. So in this period, energy and energy augmenting technical change, their numbers are biggest late 19th century, as the graph showed, whereas labor augmenting technical change and capital accumulation are dominant. Their contributions to growth are biggest in the late 20th century. And now energy, because the share of energy in output has declined, energy's contributions are still there, but they're not as big as labor and capital's contributions to growth anymore. So energy is important when it was scarce, but it's not that important anymore in terms of contribution to growth when it's not scarce. So if elasticity substitution is less than 1, as we make the energy intermediate good more and more abundant, going to infinity, then its contribution to output declines towards 0. And we think of it here. We can think of, we had a fixed amount of capital and we add more and more energy. Initially energy is adding a lot in this initial period here. We're climbing up the production function. Maybe you can see it clearer here. We're climbing up the production function to high levels of output. And then as we go here, we eventually end up pretty much parallel to this constant level of output. Adding more energy has very little effect when energy is already very abundant. Okay. Now capital's the important factor, the scarce factor, or labor that is going to contribute to growth. So it's a critical constraint industrial revolution, but much less important today as a conclusion, which kind of sad if you're an energy economist, I guess. But that's what the data say. So implications and conclusions. So now we're going beyond this historical period. So what does it tell us about present and the future? This is a solar farm in Japan, in fact. If elasticity substitution between energy carriers, between, say, primary electricity photovoltaic power, and fossil fuels is greater than 1. But if you put a cap on using fossil fuels or on carbon, this would help drive innovation to the resource that's more expandable. Because today, solar power is the more expandable resource. If you fix fossil fuels will act like the fixed wood supply acted in the Industrial Revolution. And the modern renewables, which today are using up very little land space relatively, are the expandable input like coal was in the Industrial Revolution. So that's actually a positive coming out of this research. They basically switch roles compared to the Industrial Revolution period. Energy has declined, though. Its importance in growth has declined in developed economies. So if it turns out that environmental policies do restrict energy use, this doesn't seem to be as big a deal or as critical as it might have been when energy was already more scarce. So energy is really quite abundant, making it a little bit more scarce. It has less impact today than it would have done. On the other hand, because energy is relatively abundant, we shouldn't expect to see big gains in energy efficiency, even if they're possible, as long as unless climate policy pushes them in that direction, sort of just happening endogenously, as long as energy is relatively abundant relative to other inputs like labor, because energy is not substitutable or has a low substitutability with labor. And as we talked last time, a month ago, rebound effect further reduces the contribution of energy efficiency to cutting emissions. So energy efficiency is looking here to sort of try to expand the non-fossil fuel energy supply using these levers rather than trying to get more energy efficiency. Okay. So those sort of implications, conclusion, the directed technical change can really explain well what happened in the Industrial Revolution in Britain, what happened over the course of economic growth in Sweden. We didn't use a directed technical change theory when we wrote our 2012 paper. We just came up with those results. And I found those results quite surprising. And only later, when I learned about directed technical change in about 2014 or so, in depth, I was like, oh, well, those results can be explained by the theory of directed technical change. So it really seems it's a very useful theory. There's a scope to exploit it in driving the energy transition, but it's probably very harder to use sort of that built-in incentive to drive energy efficiency improvements. You can try to drive them with explicit policy, though we looked last time, maybe that's not the greatest of ideas. Okay, so that's it. I'm happy to take questions.
Yeah, thank you very much, David. I think we have the first question in the chat.
Here. I suppose more a comment than a question. I very much agree on the need is mother of invention. I think there's one aspect missing. It's not only about the abundance of resources. I think an important driver of innovation is driver up today's geopolitics. Innovation will not only support it because people understand that new technologies needed due to scarcity, but also due to geopolitical. So I didn't talk anything about institutions. That doesn't mean that institutions and politics aren't important. So Stan textbook, why did Britain develop first? Sort of the consensus among people like Gregory Clark, who say that they could have just used wood from Scandinavia instead of British coal, is what the British institutions favoured from the 17th century on, favoured capital accumulation, protected capital, protected innovations, so forth, and there was a relative lack of war as well, which allowed if you made an investment, you knew it wouldn't be destroyed very quickly. So those institutions, relative stability after the Civil War in Britain, there were only one or two wars on mainland Britain since then, which weren't that significant. till the Second World War, when Britain got bombed, of course. Yeah, so they favoured innovation in Britain. So whereas institutions in China had a lot of coal, institutions in China up till the foundation of the People's Republic or the end of the imperial period probably didn't favour innovation in using coal. So institutions are very important, whether they're driven by profit or military, as Katharina is saying here. Yeah, so those institutions and politics are obviously very important. They need to be there. If you had scarce natural resources, lots of coal, but a terrible climate for innovation or capital accumulation, you wouldn't have an industrial revolution. So I don't think energy resources are deterministic. You need to have all these factors. But I think institutions alone, if institutions which favour this kind of development, or politics that favour this kind of development, aren't combined with the right mix of resources or abundance of resources, that right setting, nothing will happen either. So you need to think both of them. Any other questions?
Other questions or comments? I have one.
All right, good.
So you mentioned
my rescue.
You mentioned in the end that in the post-war period that labor augmenting technical change is actually what drives economic growth. So I was wondering how you can, or to what extent you can connect this to your last lecture about rebound effect and Jevons paradox. So why is it then that we have so much rebound today? So how do these two lectures connect?
Yeah, well, there is still, if you go back to the Sweden example, two things are going on here. There is still, even though the contribution of labour to growth and of capital to growth is larger than these contributions of energy, if you add up all those energy terms, actually greater, they're still greater than that of capital. But yeah, it's less important, less contribution of energy than there was. And partly that's driven because the cost share of energy has fallen, because energy has become more abundant. Energy innovation is still here. It's just not contributing as much because energy is a smaller share of total costs than labor is. So energy efficiency is improving still, but it's not the driving factor in the. If we went back to this table again, yeah, it's almost as rapid as labor augmenting technical change, but the relativity has changed over time. There's still a lot of energy efficiency innovation, improvements in energy efficiency happening. So it's not as black and white as, no, it all stopped. It didn't all stop. The relative balance and of rates of change and the relative contributions to change. Now, the rebound so there is energy efficiency improvements still. The rebound effect is based on the key factor was elasticity substitution between energy and labour and capital. If it's very, very small, near zero, then there's not going to be a big rebound, we found. Also important, here it's nearer to 1 than it is to 0. So that says rebound is likely to be quite large. On its own, that doesn't lead, in a very simple model, on its own, that doesn't lead to backfire. But we need to also consider the energy supply conditions and lots of other things to get the final estimate of the rebound effect. But here, using a very, very simple model like the Saunders models, this would suggest it's quite large because this number is close to 1 when it's close to 0. It's to 0, right? So there's energy efficiency innovation, a large elasticity substitution. So yeah, there's improvements in energy efficiency, but they don't translate into such great improvements in energy intensity as the efficiency improvements. Does that answer it?
Yes, I think that perfectly links the two lectures. Further comments, questions? So I was also wondering, you said in the end that for an energy economist, it's bad news to see that energy is actually not that relevant for growth anymore, and that energy is important when it's scarce. So do you think that due to climate change and related policies to reduce CO2 emissions, that actually we may get back to a situation where energy might become scarce?
Not in an absolute sense, as basically I'm arguing that solar power is could be super abundant, more than fossil fuels. You can power the whole world's current energy use of a fairly small area of Australian desert currently, if you put solar farms there. So I don't know, maybe we'll get fusion power yet. So no, I don't think energy is going to be scarce. What the difficulty at the moment we have is not so much availability of energy in general. It's the intermittency of fossil fuels. Oh, sorry, of new renewables. So storage technologies are the critical thing, making sure that energy is always abundant and not just when the sun's shining or the wind's blowing. So that's really, I think, more the focus now. But the actual total amount of energy could be larger than we've ever used in fossil fuels. So I don't think that's the direction we're going in.
Okay. Other questions?
But yeah, so yeah, most energy economists focus on things like climate change, but there are a lot of people in the sort of ecological economics community or whatever who still insist. People like Ayres or Kummel, these people, their insist that energy explains everything. But our research, we don't. I don't think that's. Then their models are kind of set up that way. I guess.
Okay. So there is another question in the chat.
Over access to energy is not an issue, but energy poverty still is. Yes, of course, there's inequality in distribution of energy. Yeah. But what we're thinking about in this lecture didn't get into it. We're thinking here like the aggregate economy. We didn't talk about distribution of income or distribution of output. Yeah. So energy today is very abundant overall, but of course there's inequality between countries in its use and within countries as well. So I'm not denying that. Maybe apart from a few wealthy people back in the Middle Ages, there was more equality of energy use, but at a low level.
Okay. Further comments or questions? So if not, then thank you very much, David, for the very interesting talk. And to the audience. And so let's emphasize not next week, so the date changed. So it's good to emphasize it again. The next lecture is on May 7, and it will be about the use of econometric and time series econometrics to model global climate change. So I think that will be also very interesting.
Okay, thank you.
Bye-bye.